Hello, my name is Greg Fisher from Physical Electronics. Today I'm going to talk to you about some new developments in TOF-SIMS, specifically related to TOF-SIMS tandem MS imaging with applications to monolayer characterization. So the primary difficulty in TOF-SIMS analysis concerns peak identification. In particular, as the mass to charge ratio of an ion increases, the difficulty of identification of that ion grows exponentially. In particular, at above approximately a mass to charge ratio of 150, the identification capability of TOF-SIMS alone falls apart. What we've done at Physical Electronics is a few years ago in 2016, we introduced a new instrument platform to the market that incorporates tandem mass spectrometry integrated into the TOF-SIMS instrument platform. So what this allows us to do is to get very accurate identification of ion peaks in the TOF-SIMS spectrum without in any way inhibiting or degrading the normal performance attributes or functional attributes of TOF-SIMS. In particular, what we'll demonstrate, as I mentioned earlier in this talk, is the utility of the parallel imaging MSMS for monolayer applications. The application that we're going to take a look at today is the condensation reaction of guanidine and amidine molecules onto a graphitic carbon surface. So as we see here in this graphic, the surface that we're condensing the small molecules onto is graphitic carbon, and at the edge defects, there are oxygen and hydroxyl moieties. And so in the condensation reaction, what we expect is that hydrogens from the condensing organic molecules will bind together with oxygen or hydroxyls on the surface, releasing water and therefore producing covalent bonding of the small organic molecules to the surface. So we're going to use TOF-SIMS tandem MS imaging to characterize the surface bonding. Now, before we did the TOF-SIMS measurements, there were a number of samples that were characterized using redox cycles, and the samples that we're looking at have approximately 40% of full monolayer coverage. So here we're looking at the TOF-SIMS mass spectrum, or what we call the MS1 spectrum, of the fluorinated guanidine molecules condensed onto the graphitic carbon surface. So what we can see here is that high mass to charge ratio, we have a couple peaks at 665 and 693. And what we know by doing tandem MS analysis on these peaks is that they fragment into these smaller structures that appear between a mass to charge ratio of 250 and 320. So we have focused our attention to identification, both compositional and structural analysis of these peaks in this mass to charge range. And we have been able to identify the composition and the structure of these peaks, and therefore we can also know the composition of the peaks at higher mass to charge ratio. A couple examples, I won't go through all the details of all of these peaks, but a couple of them are shown in the following slides. So here what we're looking at is in the top panel is the TOF-SIMS spectrum, or the MS1 spectrum, of the lower mass range from this sample, the fluorinated guanidine condensation sample. In the bottom panel is the tandem MS product ion spectrum of the precursor arising at a mass to charge ratio of 318. So what we can see in the product ion spectrum is a number of neutral losses that are indicated by arrows, as well as product ion peaks that are indicated by composition. So the neutral losses are indicated down in the bottom panel along with one of the product ions. Notice that the dashed lines indicate bond cleavages, and in red we have noted the atoms that comprise the neutral loss, or conversely the product ion itself. So for the precursor at a mass to charge ratio of 318, we've been able to identify the composition and the structure as shown here on the right side of the product ion spectrum. Similarly, for the peak at a mass to charge ratio of 302, we have a number of neutral losses identified, as well as product ions identified. Again, in the bottom row, the dashed lines indicate bond cleavages giving rise to the neutral losses, as well as the product ions themselves. For the precursor ion at a mass to charge ratio of 302, this inset indicates the precursor composition and structure. So to summarize what we have been able to learn using not only the TOF-SIMS data, but the article that was published in collaboration with the Massachusetts Institute of Technology, also incorporated nitrogen X-ray absorption near-edge spectroscopy and X-ray photoelectron spectroscopy, and we're able to identify the bonding that takes place from guanidine and amidine small molecule condensation onto defect edges or step edges of graphitic carbon. It was initially assumed that there would be no oxygen observed in the condensation linkages, but what we have been able to see, because the tandem MS measurements were so, is that there are some precursors that do contain oxygen, and therefore we know that the condensation reaction is not 100% efficient in the evolution of water because there is some remaining oxygen in those bonds. Further, we have been able to determine that there is no amide bonding observed, and the chemabsorption occurs predominantly via sp2 hybridized pyridinic linkages. So we've shown today, in conclusion, we've shown a new application area of using TOF-SIMS tandem MS imaging analysis for characterization and peak identification of monolayer films. In this particular case, looking at small molecules, organic molecules condensed onto an inorganic surface. For those of you interested in biological applications, the images to the right in this slide indicate 100 nanometer lateral resolution imaging of subcellular structures in single cells. And this data was published in 2018 in the journal Biointerphases. Anyone that's interested in biological applications, I would refer you to that article as a starting point. And just to summarize then here, the parallel imaging MSMS capability is simple and highly integrated, which provides a quite user-friendly experience to arrive at accurate and confident peak identifications which really for any 2D or 3D imaging application of TOF-SIMS just makes the peak identification not only possible, but really straightforward. And so just like someone would never dream really of doing an XPS analysis without using a monochromated X-ray source, it's hard to conceive these days of doing TOF-SIMS analysis without having a tandem MS capability available for not only the imaging part of it, but the confident peak identification. Thank you for your time.